Thanks for coming to my talk. I'm going to speak about fault tolerance and non-local games and present some joint work that I did with Mary Wootters and Patrick Hayden at Stanford. First, I'm going to talk about fault-tolerant computation with noisy logic gates and a connection that we formalized with amplification. And then I'll switch gears and tell you about non-local games and communication complexity. And finally, we'll show how these two areas are related, and in particular we'll construct a non-local game whose quantum win probability is determined by the requirement that communication complexity is non-trivial. We began studying these areas in an effort to understand the limits that are imposed on reasonable physical theories such as quantum mechanics by computational axioms such as communication complexity is non-trivial. And beyond our original motivation, fault tolerance with noisy logic gates is relevant for quantum computation and emerging forms of classical computation where the noise rates may be much higher than existing approaches. And non-local games are one of the most tangible settings where quantum beats classical outright. So it's interesting to see how all of these areas are related. Here are three logic gates: the AND, the exclusive OR, and the NOT gate. One of the most basic questions about these gates is, can you compute an arbitrary function with a formula of the gates? And of course the answer is yes, because this set of gates is functionally universal. In fact, you could have just used the AND gate and the NOT gate, and those would have been enough. Now let's consider adding noise. Let's add a noise parameter epsilon on the AND gate and tau on the exclusive OR gate. This means that with probability epsilon, each AND gate will fail and return the NOT of the AND of the inputs, and with probability 1 minus epsilon, it'll return the right answer. And the analogous question to before is, can you compute an arbitrary function with a bounded probability of error for a worst case input using some formula out of these noisy logic gates? And the answer, of course, is that it depends on exactly which epsilon and tau you're talking about. Here's how it depends on epsilon and tau. In the bottom left corner of this plot, you have epsilon and tau equal to 0. So that means 0 noise on either gate. And you can reliably compute here, of course, because this just reduces to the simpler case where there's no noise. But you can also compute with noisy AND gates. And you can do so even if tau is all the way up to 1/2. That is maximally noisy exclusive OR gates. And this is because, as I mentioned, NOT and AND together are functionally universal, and you can reliably compute with those gates as long as the noise epsilon is less than about 8%. In this green starry region, a series of results by Evans and Schulman, Evans and Pippinger, and Falk-Unger provide a no-go theorem that says you can't reliably compute with formulas of gates where the noise parameters lie in that square. We didn't know, though, what happened in this question mark zone, and an interesting observation by Broussard, Berman, Linden, Metaux, Tapp, and Unger was that you could reliably compute with noisier AND gates using noise-free exclusive OR gates. That's the yellow line segment on the epsilon axis. Their result stopped at 1/6, and it was unknown whether you could reliably compute with still noisier AND gates. One of our theorems is a no-go result that shows that you can't reliably compute in the orange striped zone, and in particular this rules out extending the construction of Broussard et al. Along the epsilon axis. All that's left is this little box with the question marks, and I think the techniques to finish this plot are probably within reach, so hopefully someone will come along and show us exactly what the boundary looks like between the regions of parameter space where you can reliably compute and those regions where you cannot. I won't go into any detail about the techniques that we used to show this result. But because this whole characterization is a bit complicated, you might hope that there's a simpler characterization of exactly which noisy gate sets allow for fault-tolerant computation. To study this problem, we made a new simple assumption that you can take convex combinations of circuits. So if you have some probabilities P sub I and circuits C sub I, then you're allowed to, with probability P sub I, apply circuit C sub I. With this simple assumption, we were able to show that there is a simple characterization of when you can reliably compute. And it's in terms of amplifiers. An amplifier is any circuit C such that if it's fed independent identically distributed bits that were drawn from some Bernoulli distribution that's 1 with probability P, then the probability that the output is 1 depends strongly on P about some fixed point. That is, here for the fixed point 1/2, if you input 1/2 bias bits, you get out a 1/2 bias bit. And there's also a window about that point, P equals 1/2, where if you feed in, say, 1/2 plus epsilon bias bits, you will get out, say, a 1/2 plus 2 epsilon bias bit. In other words, the derivative of the probability that the output is 1 is greater than 1 at the fixed point of 1/2. Now that we've defined what an amplifier is, a set of noisy circuits that's closed under convex combinations allows for fault-tolerant computation if and only if it contains both an amplifier away from 1/2 and a noisy NOT gate, by which I just mean a NOT sub delta gate where delta is less than 1/2. As long as you have these two ingredients, you can reliably compute. And this was not so surprising because all of the prior results that showed some positive construction of fault-tolerant computation went through amplifiers. They essentially used a small circuit that behaved as an amplifier as long as the noise rates were sufficiently low. And then they used that as sort of a noisy majority gate to amplify their success probability and keep the failure rate bounded. So our contribution was to formalize this connection. Now that I've told you about fault-tolerant computation with noisy logic gates and the connection with amplification, I'm going to tell you about non-local games and communication complexity. And then, of course, I'll show you how these areas are connected. Remember that entanglement is strictly better than shared random coins for certain tasks. By entanglement, you can imagine that there's some quantum coin that is a quantum state that's distributed in parts to Alice and Bob, and they're allowed to make a measurement of their part of the state in any basis that they wish. Whereas for shared random bits, you can imagine that there's some infinitely long sequence of uniformly random bits that's visible to both Alice and Bob. So two tasks where quantum can beat classical are non-local games and distributed computation. I'm going to tell you about non-local games by showing you the CHSH game, which is probably the most famous one. In this game, Alice and Bob receive a uniformly random input bit each, and they each must produce an output bit, and they're not allowed to communicate. They win the game only if the AND of their input bits is equal to the parity of their output bits. If they use classical shared random bits, they can win only 3/4 of the games that they play. For example, they could just both output the 0 bit. But if they're allowed to use quantum entanglement, they can win some more games, about 85% of the games. So if you haven't seen this before, this is pretty surprising. We have the classical players stuck on the left side, and the quantum players are strictly better. Note that it's possible in principle that Alice and Bob could win this game with probability 1 without being able to communicate, and we'll revisit this thought later. Distributed computation is a very different kind of task. In this kind of task, Alice and Bob are allowed to communicate at most little n bits, where little n is the number of input bits given to each player. And Alice needs to output some Boolean function of their input strings with high probability for a worst case input. The minimum amount of communication that they need in order to succeed at this task for a worst case input is the communication complexity of the function. Now, if they're somehow able to compute arbitrary functions with a constant number of communicated bits, we would say that they have trivial communication complexity. Now, if we're going to talk about computational features that we would expect to have in a reasonable physical theory, trivial communication complexity would be about as surprising as having p equals to np. So given that in both trivial communication complexity and non-local game setups, you have a constant number of bits communicated, you might wonder if these areas are related. In fact, the only difference is that for non-local games, that constant number of bits is exactly 0. It turns out that there is a relationship between these two areas, and this was shown by Cleve, Van Dam, and then extended by Broussard, Berman, Linden, Miteau, Tapp, and Unger. They showed that if it were possible somehow to win this CHSH game with greater than approximately 90.8%, then communication complexity would become trivial. So if Alice and Bob had access to some strange correlation that went beyond quantum mechanics, then they would be able, in this region, to collapse communication complexity. A natural question that remained was whether you could extend their result all the way down to the quantum value. That is, we didn't know what the communication complexity was in this dotted orange region with the question marks. Their proof was based on the fact that AND sub epsilon gates, along with noise-free XOR gates, allowed for reliable computation as long as epsilon was less than 1/6. And this is why we were interested in studying the noise threshold for formulas of these noisy gates. Recall that our tight upper bound for formulas corresponds to this orange striped box. And because that tightly meets the Broussard et al. Construction in yellow, it's not possible to extend their proof strategy in this region all the way up to quantum mechanics. Although it doesn't rule out that communication complexity becomes trivial as soon as you beat quantum mechanics at the CHSH game. But because this does cast some doubt on this proposition, you might wonder if there is some other non-local game for which any superquantum success probability causes communication complexity to become trivial. And in fact, there are many such games. For each integer k, we describe a non-local game gk such that any win probability above the quantum value causes communication complexity to become trivial. And conversely, we showed that if two players have trivial communication complexity, then there is some k such that they must beat quantum mechanics at the game gk. On a plot, it looks like this. The classical win probability is strictly below quantum mechanics, and still higher are strange super quantum correlations that would let them win more often. But any of those correlations would necessarily collapse communication complexity. I'm going to show you now how to construct a simpler version of this game where the classical and the quantum win probabilities are actually the same, but it will still have the property that beating quantum mechanics at the game implies you have trivial communication complexity. In order to construct this game, we're going to connect fault tolerance with noisy gates and amplification to trivial communication complexity in non-local games. And the key to this parallel is that we can view Alice and Bob's behavior as defining some noisy logic gate and build circuits out of their correlations. If we think about Alice and Bob as some input-output system, all of their behavior is described by the conditional probability distribution on their answers, A and B, conditioned on their questions, X and Y. For example, if we want to compute their probability of winning some non-local game, that's just the sum over all possible inputs and outputs of the probability that we would observe that input-output pair, and weighted by, of course, whether that's a correct set of answers for those questions or not. And now that we've captured Alice and Bob's strategy for playing some non-local game as the conditional probability distribution, probability of A, B given X and Y, we can turn this distribution into a noisy logic gate. And here's the prescription to do that. If Alice and Bob have some strategy, say on 2 input bits each, then we define the Alice-Bob logic gate with 2 input bits. The actual questions x sub I and y sub I are chosen uniformly at random, but subject to the constraint that xi plus yi equals zi mod 2. And then the output bit of the logic gate is just the sum mod 2 of their output bits A and B. And it turns out that if Alice and Bob have access to some correlations that give rise to some logic gates by this prescription, then they can simulate arbitrary circuits of those logic gates with only a constant amount of communication. And now we're going to define our non-local game GK such that if you can beat quantum mechanics at the game, then that logic gate I described will serve as an amplifier away from 1/2. So let's fix an integer k. Then Alice and Bob will each receive 2k plus 1 input bits from some special probability distribution pxy. They aren't allowed to communicate, and they each produce an output bit A and B. The players win if the majority of the element-wise sum of their input bit strings, mod 2, is equal to the parity of their output bits. It turns out that for some special choice of the input distribution, any win probability for this game above the quantum value implies that this Alice-Bob gate serves as an amplifier away from 1/2. And they can also simulate a perfect NOT gate. For example, Bob can just flip his input bit and return it. So together with the amplifier, by theorem 1, then this implies that there's fault-tolerant computation by the circuits of Alice-Bob gates. And because, as I mentioned, Alice and Bob can simulate arbitrary circuits of Alice-Bob gates using a constant amount of communication in shared random coins, then this implies that communication complexity is trivial for such Alice and Bob. Therefore, any win probability for the game above the quantum value causes communication complexity to become trivial. And in other words, the quantum win probability of the game is precisely determined by the requirement that communication complexity be non-trivial. Here are my references, and thank you for coming to my talk. I hope to see you at the question and answer session.